Imagine you are standing in your chemistry lab. It's the day of your practical exam,
The pressure is on.
and the external examiner is watching you like a hawk. On the bench in front of you, there are two bottles. Both have a clear liquid inside.
To the naked eye, they look exactly the same.
Exactly. Both bottles contain a chain of 3 carbon atoms, 1 bromine atom, same formula. But here's the catch.
There's always a catch.
If you pick the wrong one, your experiment fails. Completely. One of them, explodes into a reaction instantly.
Huh.
That SN2 mechanism we study.
And the other one?
The other one just drags its feet. It reacts slowly or does something else entirely. How do you know which is which?
That is a very real scenario and honestly a nightmare for any student during practicals. The answer, of course, lies right there on the label.
The name.
The name. Welcome to another deep dive. Today we're unpacking a topic that might seem simple on the surface, but is really the foundation of how we communicate in organic chemistry.
We are discussing nomenclature from Unit 6, haloalkanes and halorines.
That's right.
Okay, let's be honest for a second. When students see nomenclature in the syllabus, most of them just shuck. They roll their eyes.
Oh, I've seen it many times.
They think, sir, this is just ratification, right?
Yeah.
Just memorizing a bunch of dry rules to get a few marks in the board exams. Why should I care about this beyond the exam hall?
I get that sentiment. It feels like, administrative work, but frankly, it is so much more than that.
Okay.
Nomenclature is really about two critical things: communication and safety. We need to explore this to prevent lab accidents, like picking that wrong bottle, and of course, to ensure you get the full marks you deserve.
That's true. You know how strict the board marking scheme is? A tiny error in the name.
And the entire answer is crossed out. You miss a number, you lose the mark. It's that simple.
So let's start from ground zero. Let's break this down to the simplest level possible. When we talk about nomenclature for haloalkanes, what are we actually doing?
At simplest level, nomenclature is just the systematic naming of compounds using IUPAC rules.
But here's something that always confuses me. For alcohols, we change the suffix, right? Propane becomes propanol.
Yes.
For aldehydes, it becomes copanol. But in haloalkanes, the parent name is just propane. Why doesn't the halogen get that VIP treatment?
That is a brilliant question, and it's the root of so much confusion. The thing is, halogens chlorine, bromine, iodine are considered, well, relatively low rank.
Low ranking?
Yes. They are treated as substituents. Think of them like a guest or a side branch attached to the main hydrocarbon chain. They don't have enough rank to change the family name.
So they're always a prefix, like chloro or bromo.
Always a prefix.
Yeah.
So to visualize this, just imagine a simple hydrocarbon backbone, say a chain of 3 carbons. Propane.
Okay, got it. Propane chain.
Now imagine taking away one hydrogen atom and replacing it with a halogen, let's say a bromine atom.
All right, so I've stuck a bromine on. It's like a little flag sticking out of the chain.
Exactly. But now, here's the critical question. Where did you put that bromine? Did you attach it to the carbon at the end of the chain? Or the one in the middle?
So you have to specify the location.
You have to. And this brings us to what's really happening. The IUPAC name, it assigns a unique, unambiguous identity to the molecule. We specify the position because that location, it determines the chemistry.
It determines the carbon type, right, and how crowded the molecule is.
Precisely, the steric effects. So if we need an exam-safe definition, it would be this. IUPAC nomenclature for haloalkanes names the halogen as a substituent, using a prefix like chloro or bromo on the parent alkane chain.
With the halogen's position number indicating which carbon bears the halogen.
Perfect. That position number is everything.
In fact, our sources mention a misunderstanding trigger line here. Students so often fall into this trap. They just write bromopropane and think they're done.
That is a classic mistake. I see it on answer sheets every single year, saying bromopropane is ambiguous. It's just wrong.
It's like saying I live on Gandhi Road without the house number.
Exactly. Are you at number 1 or number 2? In chemistry, saying 2-bromopropane is precise. It's correct. Without the number, you haven't actually named the compound.
Fair enough. Ambiguity loses marks. I really like that address comparison. Let's expand on that. The sources call it the address system.
It's a great way to remember it.
Okay, so think of the IUPAC name as a postal address. First, you have the halogen type.
That's your street name. Bromine Street or Chlorine Avenue.
Then you have the position number.
The house number. Number 1, number 2.
And finally, the parent chain.
That's the town name. Propanville or Butane City.
I love that. So just as 42 Main Street is a totally different place from 12 Main Street,
0.2 bromopropane is a totally different molecule from 1 bromopropane.
Even though they're in the same town, Propaniaville, on the same street, Broman Street, the house number changes everything.
And it's worth understanding why this system exists. Historically, before IUPAC, it was just chaos.
Common names, right? That's a headache for students, too. I remember struggling with isopropyl chloride versus 2-chloropropane.
Ah, yes. Isopropyl chloride is the common name. 2-chloropropane is the IUPAC name. They describe the exact same molecule.
So which one do we use in the exam?
For nomenclature questions, always stick to the IUPAC address system. You need to recognize the common names, but IUPAC is the rule.
Okay, let's do a quick mental movie to make this stick from the picture this section.
Let's do it.
I want you to imagine that carbon chain again, but this time, see it as a row of numbered houses on a street. House 1, House 2, House 3, and so on.
Okay, got the street.
Now, imagine the halogen, let's say bromine, is a bright red flag.
A red flag, okay.
If you plant that red flag at house number 3 on a 5-house street, what's the address?
That would be 3-bromopentene.
Right. But if you pull that flag out and move it to house number 2...
the name changes. It becomes 2-bromopentane. The visual really emphasizes that moving the flag, the halogen, changes the fundamental identity of the molecule.
But wait, what if there's a conflict? This always trips students up. Say I have a double bond at one end and a halogen at the other. Who gets the lower house number? Who's the VIP?
Ah, the priority war. This is crucial for Class 12. In the IUPAC hierarchy, a double bond has higher priority than a halogen.
So the double bond wins.
The double bond wins. Remember, halogens are just guests. Double bonds are part of the family infrastructure. You always start numbering from the end closest to the double bond.
So even if that gives the bromine a bigger number, say 5?
Even then, the name would be 5-bromopent-1-endo. The double bond dictates the numbering direction, not the halogen.
That is a vital distinction. Now let's go back to those 2 bottles from the beginning. You said one reacts instantly and one doesn't.
Exactly. This is the observable phenomenon. Let's compare 1-bromopropane and 2-bromopropane.
In 1-bromopropane, the bromine is on the first carbon, a primary carbon.
Right. At the end of the chain, it's very open, very accessible. It will undergo an SN2 reaction very, very rapidly. That's our explosive one.
And 2-bromopropane.
The bromine is on a secondary carbon. That carbon is more crowded.
You mean steric hindrance.
Exactly. The neighboring methyl groups are blocking the way. So it reacts much slower via SN2. It might even try an SN1 reaction. The mechanism completely changes just by moving that number from 1 to 2.
Wow. So the name literally encodes the reactivity. And this isn't just theory, is it? There's a real-world application here.
A huge one. In pharmaceutical synthesis. When companies patent a drug, accuracy is a legal requirement.
Oh, absolutely. When they file a patent for an active pharmaceutical ingredient, they must use the exact IUPAC name.
A spelling error, or worse, a wrong position number, could invalidate the whole patent, or it could lead to a factory synthesizing the wrong chemical.
Imagine manufacturing tons of the wrong medicine because someone wrote 3-chlorophenol instead of 4-chlorophenol.
It's a high-stakes game, and this leads to a common counterintuitive thought students have.
Okay, what's that?
A student might think, look, 1-bromopropane and 2-bromopropane have the same atoms. They should behave the same. The number is just a formality.
But the reality is...
they are completely different compounds with dramatically different reactivity. Why? Because position determines carbon type primary versus secondary, and carbon type determines the reaction pathway SN2 versus SN1. The number isn't arbitrary. It reflects chemical reality.
Okay, I think we've established why this matters. Now let's get practical for the board exams. Can you give us the exam-safe clarity lines?
Let's do it. Clarity line 1. Remember, the halogen is a substituent. It's a prefix, not a suffix. The parent name remains alkane.
So do not confuse this with alcohols where the suffix changes to -ol. Got it. Next.
Clarity line 2 is the lowest number rule. Always number the chain from the end that gives the halogen the lowest possible number.
What about the tiebreaker? If the numbers are the same from both sides, say a bromo at 2 from the left and a methyl at 2 from the right.
Excellent question. If the numbers are a tie, then you look at alphabetical order. Bromo comes before methyl, so bromo gets the lower number. It would be 2-bromo something.
Okay. Lowest number first, then alphabetical. What's clarity line 3?
Position number is mandatory. I cannot stress this enough. Chlorobutane is not a name. It is a guess. 1-chlorobutane is a name.
Right. No number, no name, no marks. What about multiple halogens?
That's clarity line 4. Use D, try, etc. But here's the key. You must repeat the number. If you have 2 bromines on carbon 1, it is 1-nor-1-dibromopropane.
Not 1-dibromopropane. I see students make that mistake.
Every halogen needs its own house number, every single one. And that brings us to clarity line 5, which is alphabetical order in the name itself.
So if you have chlorine and bromine,
Bromo comes before chloro in the name, always. Even if chloro has a lower number, like 2-chloro-4-bromo, you would write it as 4-bromo-2-chloro because B comes before C.
that is tricky. The numbers decide their position, but the alphabet decides the order you write them in.
Precisely. And we can't forget the benzene rings.
Halorines.
Yes. Clarity line 6, halorines. You can use numbers 1 and 2 or 1 or 3, but you must also know the common system.
Ortho, meta, para.
You need to know that ortho O is 1 more 2, meta M is 1 more 3, and para P is 1 more 4. The question paper will use these terms.
So if a question asks about the melting point of the P-isomer, you have to know that means the 1-4 isomer at opposite ends of the ring.
Exactly. The nomenclature is the gateway to the theory.
Okay, that was excellent. Let's do a very quick, high-energy summary.
Let's do it. First, the core idea. Nomenclature names the halogen as a substituent, a prefix, and the position number is mandatory.
Second, the image. Think of the address system, house number, plus street name, plus town name.
Third, the example. Remember, 1-bromopropane versus 2-bromopropane, same atoms, different position, totally different chemistry.
Then finally, the ultimate exam tip.
No number, no name. Precision is key. And remember, the priority war. The double bond is the VIP, not the halogen.
That's a great summary. Before we sign off, any final thought for our listeners?
I do. I want you to realize that every IUPAC name you write, it's a claim. It's a prediction about a molecular structure.
How so?
When you write 2-bromo-2-methylpropane, you aren't just writing words. You are predicting this molecule has a tertiary carbon. You are predicting it will favor SN1 reactions. You are predicting its behavior.
It's the language of chemists.
It is. If you get the name right, you're actually predicting the molecule's future.
That is a powerful way to look at it. Not just a label, but a prediction. Well, thank you for joining us on this deep dive. Next time you see a chemical name, try to visualize that street and house number. Practice a few on your own. From both of us, all the best for your studies.
Happy studying.